this session on transient stability. We have this afternoon 6 papers on the topic. The first paper is entitled Excitation Control Method Based on Wide Area Measurement System for Improvement of Transient Stability in Power Systems. And the paper will be presented by Mr. Kenichi Kawabe. Mr. Kawabe, please go ahead.
So hello everyone. I'm Kenichi Kawabe from Tokyo Institute of Technology. I'm going to talk about a novel excitation control method based on wide area measurement system for improvement of transient stability. In this presentation, I will show that the WAMS can help the excitation control to further improve the transient stability. Here is the outline of my presentation. First, I will start with background and purpose of this research. And then I will talk about the overview of a proposed excitation control method using wide area measurement system. After that, I'll show some numerical examples that demonstrate the effectiveness of the method on the transient stability. And finally, I'll conclude with the summary and future works. So let me start with the background and motivation. The application of excitation control system to synchronous generators have been a traditional solution for transient stability improvement. However, we think there is still room for improvement in the excitation control. First, there are trade-offs in the effectiveness of the AVR and PSS in controlling the first swing stability, because the PSS tends to override the voltage signal to the exciter. Second, we can make further use of the control range of excitation system for generators distant from fault location, because those generators does not change the excitation voltage so much when we apply the conventional AVR and PSS. In order to further develop the excitation control system, we have studied the application of wide area measurement system to the excitation control. We recognize that there are still technical challenges in adapting WAMS, but WAMS has a potential to overcome these weak points. The purpose of this research is the development of a WAMS-based excitation control method for transient stability improvement. The main advantage of the method can be summarized like this. First, the method can improve the first swing stability that the PSS cannot improve. Second, the method can make use of the excitation control for the generators distant from a fault location. I'll talk about them later in this presentation. Now, I'd like to talk about the overview of the excitation control method using wide area measurement system. This slide shows the configuration of the proposed excitation control. In the method, WAMS-based stabilizer is proposed and applied with the conventional AVR. In the WAMS-based stabilizer, excitation voltage is controlled by using the wide area data, such as rotor speed and internal voltages of all the generators in the system. The next slide shows the block diagram of the proposed method that I showed in the previous slide. As you can see, it consists of the AVR and the WBS. The WBS outputs the additional input signal to the AVR. Here, the WBS stands for the WAMS-based stabilizer. Now, let me elaborate the WBS in the next slide. In the WBS, we calculate sensitivity coefficients by the wide area data acquired in the real time. The sensitivity coefficient represents the change in the time derivative of each generator output with respect to the change in the excitation voltage of each generator. Then the WBS calculates the additional control signal to the AVR to speed up the decrease in the energy function after the fault. In the block diagram, you can see the additional control signal to the AVR is calculated by the rotor angle, rotor speed, and the sensitivity coefficients. Now I will move on to the numerical examples. We verify the effectiveness of the proposed method for a multi-machine power system, modeling western part of Japanese power system. A 3-line to ground fault is assumed, and 3 cases are conducted as shown in the table in the bottom left. The generators equipped with the AVR in all cases. The PSS and the WBS were applied in cases 2 and 3, respectively. In case 3, we set the latency to 100 milliseconds in applying the WBS. First, let's take a look at the effectiveness of the PSS on the first swing stability. The figure on the left shows the rotor angle deviation when we apply the AVR. On the other hand, the figure on the right showed the result with the AVR and the PSS. As you can see, the generators step out because of applying the PSS. By the way, it is a common sense that the PSS is effective for the damping enhancement. This is indicated from the comparison of the critical clearing time shown in the table. As you can see, CCT is extended by applying the PSS. This is because the PSS improves the end swing stability. In other words, the PSS prevents the generators from stepping out after the first swing. Let's move on to the next comparison that shows the effectiveness of the WBS. As seen from the figure on the right-hand side, the first swing stability can be improved by applying the WBS. You can also see that the WBS enhances the damping of the subsequent swings. Moreover, the comparison of the CCT shows that the WBS is more effective than the PSS. The next slide shows the comparison of the excitation voltages. The top graph shows the result when we applied PSS, and the bottom graph shows the result when we applied the proposed method. This graph shows the generators near the fault location change the excitation voltage in the positive direction. This control action is mainly triggered by the AVR because the voltage drops near the fault location. One of the significant differences is the control action circled by the blue line. In the case with the WBS, Some generators change the excitation voltage in the negative direction after the latency of 100 milliseconds. They are the generators far from the fault location. In the next slide, let me explain the effect of this unique control action. The top figure is the single line diagram of the test system that I showed earlier. Contrary to the fault location in the top left, these generators change the excitation voltage in the negative direction, which I already said. These control actions decrease the voltage of the generators. Thus, the generators accelerate owing to the control action. As a result, the rotor angle of the generators near the fault location get closer to the other generators. This is one of the reasons the WBS is effective for the improvement of the first swing stability. So far, we have seen that the proposed WAMS-based stabilizer can suppress the first swing and the subsequent swings. However, there is a concern that the latency can deteriorate the stabilizing effect. In the numerical examples so far, we set the latency to 100 milliseconds. In the next slide, we set the several lengths of latency to study the impact of their latency. The graph compares the rotor angle deviation of the generator near the fault for several lengths of latency. Contrary to the result with PSS shown by the blue line, the damping is low when we set the latency to 500 milliseconds. These results indicate that the WAMS technologies such as high-speed communication play an important role in the development of the proposed method. We also think it is important to develop a substitution approach, such as an event-based excitation control method. In conclusion, let me go through the main points again. The WAMS can help the excitation control system to improve the transient stability by adapting the proposed algorithm. One of the main advantages of the method is the effectiveness for the improvement of the first swing stability. Even if the control generator is distant from the fault location, the control of its excitation voltage contributes to the transient stability improvement by applying the proposed method. It is also confirmed that the latency has a significant impact on the damping enhancement. Therefore, in our future work, we will develop an event-based excitation control method using wide area data acquired in the normal state, which can be a substitution approach for the response-based method presented in this paper. Thank you for your listening.
Okay, thank you very much, Mr. Kawabe. Thank you for your excellent presentation. I must admit that my paper, which will be the last paper of the session, addresses a similar problem, and we are suggesting very close approach to yours. But first, do we have any question from the audience?
Yes, we have. If you go to Q&A, there's 2 questions there.
Okay.
Okay.
So, can I repeat the question first?
Yes, please.
Okay. The first question is, why choosing WAMS technology for communication when comparing to standard internet. For example, optical fiber with low latency. Would WBS having security issue? For example, being hacked? Yes, that's a good question. I think regarding the security issues, I think it's a very important and challenging task that we have to overcome. But in this paper, we haven't considered the security problem, and this audience also asked about the reason for choosing the WAMS technology. Okay, and the reason for choosing the WAMS technology is explained in this slide. So we have two purposes to adapt the WAMS. One purpose is the improvement of the first swing stability. The conventional PSS tends to cancel the voltage signal from AVR. So we think that by monitoring the state of all the generators in the system by WAMS, we can decide better control action of the excitation control. And the second motivation for using the WAMS technology is the full utilization of the generators, control range of the generators distant from a fault location. When we apply the AVR or PSS, generators near the fault location tends to change their excitation voltage. On the other hand, generators distant from the fault location does not change the voltage so much. So in order to fully make use of the excitation control, excitation voltage, we apply the WAMS technology. So that's the reason for adapting WAMS. And can I move on to the second question?
Well, just go to the second and try to answer the third question. Just writing through the chat, please, because we have only 5 minutes for questions.
Right. Okay.
The second, and then.
Okay. The second. Okay. The second question. Actually, there are two questions. So first, I repeat the first question. The first question is, how do you calculate the sensitivity coefficients? Okay, so the detail is written in the paper, but I also have a supplementary slide. This is a slide for explaining the overview of the sensitivity calculation. The more detailed definition of the sensitivity coefficient can be represented by this equation. So as you can see, the sensitivity coefficient can be calculated by using the admittance matrix and the internal voltage of all the generators. And the most difficult part is the calculation of this partial differentiation. And here, I show only the result of this partial differentiation of the internal voltage. As you can see, this part can be calculated from the machine constant and rotor angle. So that's why we need the rotor angle to in this in this control system. And this equation is derived from the mathematical expression explained in this famous book. Okay, so that's the, I think we don't have enough time to answer the remaining questions. So should I finish?
Yes, thank you very much, Mr. Kawabe. So,
okay, thank you very much.
Thank you very much.